Hello, section 1.6, the paper computer. Piccone, Garbini and Devine helped me write this book. It's pretty cool. MIT Press published it. rtcbook.org's got the companion website hosted. Okay, short lecture, but fun. I think this is a really fun one. I always enjoy teaching this material. Introducing the paper computer. The paper computer is a representation of a subset of a computer's registers and memory through time. Okay, sequential states through time. In this section, we will examine a paper computer for an ARM processor to better understand our ARM programming model. The operation of the ARM processor will be explored by examining the execution of each step in a simple program. Okay, so here's an example program. It's very simple. So it's written below in the ARM Unified Assembler language. So we've got a few different instructions here. Let's take a look at them. The first two instructions use opcode mnemonic LDR, which loads data into a register. So load register LDR. It loads into register R1, so the first argument, from memory address labeled augend. So you can label memory addresses, and augend is where we're going to go look for this data to load into the register. We use it again, so load from addend to register 2. We're going to load data from two different addresses into registers 1 and 2. Next, we are going to use the adds opcode mnemonic. So this instruction takes the sum of R1 and R2, the contents of register 1 and register 2, and saves the sum to R2. So it adds these two and it sticks it in where R2 is, overwriting what was in R2. Okay, str. This instruction stores the contents of register R2 in the memory with address sum. So that is the store instruction. Here is a label for this instruction, and this instruction is no op. So it does nothing. The label here is used in the branch instruction, which is next. So B is the branch instruction, and when you give branch a memory address or a label for a memory address, it will move the program to the location of that address, which would be there, and we would go in a loop infinitely. Those last two instructions will be repeated endlessly. So a very simple program. Loads some data into registers, sum that data up, temporarily store it in register 2, then store it in the memory with label sum, and then do nothing repeatedly. Okay, that's our simple program. Let's see what this would look like. So let's say we have our program loaded up into memory. We have these memory addresses here. Notice that the addresses go every 4. So we have a byte at memory address 10000, and so 05 is the first byte, and then at memory address 10001 we have 00, 200, 300, and then the fourth one is labeled, or the fifth one, but number 4 is labeled. FB is the contents of that byte. So this is a very common way to represent 4 bytes and the memory addresses that increase. So each byte gets its own address. We're only listing every 4, however. So memory address is the first column. The memory content is the second column, as we saw. So we have 4 bytes, 32 bits. We have the instruction mnemonic here, also the memory contents of its data in this column, and then we have a comment. So in these first two addresses, we have data stored. So these are going to be the data that will load in to the registers to sum together. So we have those here first in memory. And then we're also going to put the sum in this location. We start off with memory contents all ones, just because we want to see what happens when it changes. We want to see it change. So we're going to load it up into all ones to start. And then after that in memory, we have our program. We don't have to have our data right next to our instructions in memory. It's just convenient to have it that way for the purposes of the paper computer. Okay, so this is the same program that we saw in the previous slide. It works in the same way. It's just that now we see the memory content that describes each of these instructions. So we didn't list those before, but the mnemonics that are given over here, like LDR and ADDS, these have opcodes, and then also the register signifiers. They also show up over here in the memory contents. So these are encoded into machine code in the memory contents. And in this column, we have the mnemonic, which is a little easier to read, which is why we use the mnemonics. Okay, so this is our program in memory, and along with the data. Okay, so this table is going to show us columns that correspond with the states of the registers that we are interested in and a couple memory addresses. So here, actually just one memory address, the sum. So if we go down this first column, this is the initial state. We have the sum label in memory, all ones, right? So there was our memory content, all ones. That's where it is showing up in this table. And we have register 1 and register 2. Let's say those both start off with zeros. Doesn't really matter for the purposes of our program because we're going to overwrite them anyways, but let's say they start off with zeros. And the program counter, which tells us where we are in our program, we are at 1000C, which is right here for our initial state. So state 1, we're at this instruction. The application status register, we have none of these application status register bits are flagged at this point. So N, Z, C, V, and Q, these have to do with carry bits. When we do arithmetic operations, is the result 0, etc. So none of these flags are activated, so they're all zeros. And the instruction pipeline as well. So the instruction that is in the program counter is the one that's corresponds to this next guy up. So 14, 10, 1F, E5, 14, 10, 1F, E5. That's the next instruction. So our program counter is here. So what's next in our instruction pipeline is this instruction, which is the load to R1. So we execute this instruction, which is given here. So the machine code for it is given here. And that instruction takes us from state 1 to state 2. In state 1, we had register 1 was 0. Now we've loaded data from the, if we look up here, we loaded data from augend into this register 1. Augend had 05 in it, and now we have 05 in our register 1. The highlights show changing values from one column to the next. What also changed, the only other thing that changed, was that the program counter was incremented. So now we've gone to the next instruction, which is at here. So PC here, now it's here. Okay, so this is our next instruction. It's another load register. We're loading a different piece of data. into a different register. So very similar looking machine code because they're very similar instructions. So we load the data from addEnd, which is F's and B, so F's and B, into register 2. Okay, increment the program counter, 14. All right, so now we're here. And this is our instruction, which is to add the contents of registers 1 and 2 and save the result in register 2. So in the next column, that takes us to the column 4. The next column, we have summed registers 1 and 2 together, so 5 and FFFFFB, and we got the result and we stored it in register 2. The result was 0, okay? So I contrived it to be 0 because I wanted to see 0, that flag gets set in the application status register, and the carry bit also, because we've overflowed the representation. We've just overflowed the representation. F is the last digit in hexadecimal, right? So we're almost full with this 32-bit representation, and we've added 5 to B, and we've just overflowed. So we've carried in this operation. And that carry application status register is the indication that we have done that we've overflowed. Okay, now we've done this. So that got us to 4. So after 4, we are going to store what we have in register 2 to the sum label in memory, which is, remember, this first row. So we store that 0 from register 2. We store it in this row. So this gets stored there. And every time we increase the program counter. So that was this opcode. Now in state 5, we're going to do a no operation, which does nothing. Okay, so we go immediately to 6, which goes back the program counter back to 5. So program counter in state 6 is 20. So there's our 20. In the pipeline, we have this instruction. And that instruction is to branch back to 1001C. So that's what we do, and we get our program counter back to 1001C, and then this is going to repeat again. So then the next one will be program counter will be 20 at 10020, and then it'll go back to 1001C. So we'll just go back and forth between these two states thereafter. So this has been the paper computer. Go through it in detail. It's also in the section in the book. It explains it in a little bit more detail. Also in the section is a description of how a single instruction can be understood and how it operates in the processor. So yeah, try writing another program just using assembly language like we did here. The ARM documentation has all of these mnemonics, and you could write a program that does something like this. So, okay, that's all I have for today. I'll see you next time.